Maximum and minimums. Okay, so what I'm going to do right now is just going to give a step-by-step how we're going to do it, and then show a couple examples of how to find extrema, which is another way of saying max or min. Okay, so step number one when we're doing this is we've got to find our critical points. And what I mean by critical points are we take the derivative, we set that derivative equal to 0, and then we solve. We're looking for when the derivative is equal to 0. Remember on the roller coaster, when we're at the top of the roller coaster or at the very bottom of the roller coaster, either way, we know we're at those positions when our derivative is equal to 0, when we get a slope of 0, when we're no longer going up or down. That happens when our slope is 0. And remember, algebraically, another way for saying slope is our derivative. So that's why we set it equal to 0. Step number two then is that we have to check our intervals for increasing, decreasing. Because when you're on the roller coaster and you're going to the top, you're finding that maximum height. You're going up and then you go down. Your slope is positive and then your slope is negative. How do I know when I'm at the bottom of the roller coaster? Because I'm going transition from going down to going back up. So when you're at the bottom of the roller coaster, you're zooming down to it, your slope is negative, and then you level off, and then you start going up again. So it's a transition from a negative to a positive slope. So that's what we'll be checking. And then step number 3, don't forget about your endpoints, because another area where you could have your max or min is at the end of the roller coaster ride in that one example I gave. Okay, so here's our first example. We're doing the function f of x is equal to 2x to the third minus 6x plus 3. And we're going from the interval from -3 to 1.5. We're including those x values, those endpoints, and so we need to check them. All right, first thing we want to do is we want to take the derivative, we want to set it equal to 0, and we want to solve. So I'm taking that function, going to take its derivative. Just remember that the derivative of a plus 3 is 0. That's why you don't have that 3 went away. Derivative of 6x is 6, and the derivative of 2x to the third is 6x squared. And that's what we have. So we're going to next step there is take that, set it equal to 0. So I'm just taking the derivative there, that's 6x squared minus 6. I set it equal to 0. And now I want to solve for that. So how about if we bring the 6 over by adding 6 to both sides and then divide both sides by 6. So a little two-step process to get my 1 equals x squared. And then let's take the square root of both sides, and then remember that we have two solutions, so we get a plus or minus. So our critical values here are -1 and 1. And so then what we do is we take those two critical values. We've got our derivative. We set it equal to 0. We got plus and minus 1. Then what we do is we kind of make up a number line. We put our x equals -1 spot, our x equals 1 spot. And so now what has happened is our two critical values has separated the number line into 3 sections. So we're going to have to check these 3 sections for when they're increasing, when they're decreasing, because that's what's going to happen on our graph. So we want to know when the derivative is positive and when the derivative is negative for these intervals. So what we have here is arbitrarily, I'm just picking a number. I'm picking -100. So I take that -100 because what I'm doing is I'm checking this left section here to see whether the derivative is positive or negative, whether our slope is positive, negative, whether we're increasing or decreasing. And what I do is I pick a number because it's like the Three Musketeer principle. If it works for -100, if -100, when I plug it into the derivative, it comes up with a positive result, then all of these numbers in that interval would be positive. If -100 ends up being negative, then all the numbers in this interval here on the left-hand side will end up being the same negative. So basically, we take a number that you pick out, you plug it in here into our derivative. Notice that this is a power 2, so that's automatically going to make 100 squared. They're going to make that result positive. You multiply by 6, you subtract by 6. That number is going to be positive. So just go ahead and crunch that out in your calculator. I really don't care the actual number. It's just whether it's positive or negative. negative. I just want to know whether the derivative is positive or negative, so whether I know it's increasing or decreasing. And so what we're going to do is we get a positive result, and so that I go now to the next interval, and I'm playing with between -1 and 1. I pick my favorite number. Well, it happens to be 0 here. And so I take 0, I plug it into this formula here, this derivative, and I end up getting -6. It's a negative value. That's the key thing. It's a negative value. So then what I do is I go to the third section over here. I pick my number that whatever number you want. I just happen to pick 137. You can pick any number that's bigger than 1. You plug in 137 here, square it, multiply by 6, subtract 6. You end up with a positive number. And so what I have here are the values of my derivative. And the left side here, all my numbers. You pick any number here in this interval on the left-hand side, and you will get a positive for my derivative. You pick a number in between -1 and 1. I don't care what you pick. Go ahead and pick your favorite number. Plug it into the derivative. You're going to end up with a negative number, guaranteed. And then when we go to the right interval here, pick a number. I picked 137. It came positive in my derivative. You can pick any other number that you want. It will end up being positive. How do I know that? Is because we found where the derivative was equal to 0. Those are our critical values. Now you see why they're called critical, because they're really making our intervals, they're really making our number line really easy to kind of work with. Okay, now what does this mean? How do we work this? Well, when I got a positive slope here, I basically am envisioning my graph to be going up. So I know it's kind of curvy a little bit, but I know for everything to the left of -1, that graph is going up. And then for the part of the graph between -1 and 1, our slope values are negative because our first derivative is negative. That means our original graph is decreasing, is going down. So the original f of x graph, way up here at the top here, f of x, between -1 and 1, this graph will be decreasing, will be going down, because it has a negative value for the derivative. And then for that third section over here, I'm seeing a positive sign. That's a positive sign that we got from the derivative. That's meaning our graph will have positive slopes. That means that graph's got to be going up. So basically what I'm looking at is a graph that's going to be doing this kind of up and then down and then up kind of graph. I know I'm using straight lines right here, but hopefully you can imagine the curve that will happen along with the original graph. So that meaning that I've got a potentially right here at x equals -1, I've got a potential max, and for at x equals 1, I've got a minimum. Whether it's an absolute maximum or a relative minimum, that's what we're going to find out. So I got a step number 3, check my endpoints. So basically what I'm doing here is I'm taking the 3, I'm plugging it into the function, crunching it out, I get -33. And then I have the two critical values, my -1 and 1 that we got when the derivative was equal to 0. Plug those in, got 7 and -1. And then I take the other endpoint, 1.5, I plug it into the formula, crunch it out, and I get 0.75. So now what I have are the 4 main key points where any max or min is going to happen. It's going to happen when the derivative is equal to 0 or at the endpoints. And so at x equals -3, we got a y value of -3. That's going to give us the absolute minimum. There is no y value that's going to be less than -3 in this interval. For our next critical point, we have -1 here for our x value. We get a y value 7. What we have here is an absolute maximum because there is no other y value that is larger than 7. For our next one, we have a relative minimum because why do we have a relative minimum? Is because back up here, there's a -33. That was the smallest y value, lowest y value we could have. This -1 here, it just basically is close, but it's only a minimum for a small area around it. And then our last one at 1.5, our endpoint, we have 0.75, and that's a relative maximum. Because for a small neighborhood around 1.5, it's the highest point. So what does this look like? If I were to look at the graph here between -3 and 1.5, you see that the graph has a low point here at -33. And then it increases. We knew that because the derivative was positive. We get to -1 here, and we have the absolute maximum because there is no part of the graph here that we're playing with that is higher than at -1. And then it decreased, got to this relative minimum. It's relative minimum because for the small area around it, it's the lowest point. It's not an absolute because we have lower points here to the left side. So it's a relative minimum. And then over here at the very end point, it's a high point for this area around here, but it's not the highest point overall. The highest point overall is back over here at -1. So this one we'll call a relative maximum in a way. Okay, and so that's how we play this game. Now, do have to be careful with you. The term that I'm using for relative mins and max, there are some some math teachers that only like to use relative for when the derivative is equal to 0. I'm using it kind of loosely, basically making a distinction between the absolute and the relative. So basically, relative to me is being the highest point or lowest point for a small neighborhood. You get that when the derivative is equal to 0, or you get that when you're an endpoint. So very loosely on the relative. Okay, so that kind of starts us off. I will do some more examples in the next part. Thanks, and have a good day.